Hello, everyone, and welcome to PChem. So today we're going to be trying to find a good equation that will help us describe a real gas system. So as we previously described, we run into a slight problem when we use a uh, ideal gas law equation, because it turns out that in order to deal with gases under high pressure, low temperature conditions, we often need to build in our fudge factor of Z, which is our compressibility coefficient. The problem is, except for empirical measurements, we don't have a lot of good data on how we get to this Z factor. So it turns out that physicists have lots of tricks of how to take an equation that works under limited circumstances and try and expand its usefulness. One of the most classic tricks that physicists love to make use of is a Taylor series. Yep, that's right, Calc 2 with a vengeance. So the idea of a Taylor series is you take a correction factor and you try and expand it as a series of as a power expansion. So what we're going to do is replace Z with a power expansion about 1, the ideal value, with respect to the molar volume. And when you do this, what you get is what's called the Virial equation. So we have uh, the original value, our A coefficient, which we know should ideally be 1, because if the system behaves ideally, our Z should be 1, and we end up getting the ideal gas law back. However, at very small molar volumes, what we're going to see is increasing power of the exponential of the additional terms. And so again, in this power expansion, really what we're doing is treating our power expansion terms as our Z coefficient, or our compressibility factor. And what ends up happening is that as my molar volume ends up decreasing, each one of these terms is going to become more and more important. At very large Z's, all of these coefficients are actually quite small. However, Z starts becoming as my molar volume starts becoming a little bit smaller, then because I'm dividing by a small number, this term will start becoming more and more important. And then as my molar volume decreases even more, this term will start becoming even more important. And then when I get to really small volumes, I need to use the full third order corrections. So again, this will be a set of terms I'll often make use of. We have our original value, a first order correction, a second order, a third order, and a fourth order correction. So this is one of the reasons why we make sure that we cover Taylor series in Calc 2, because it's a very powerful tool in taking a simple model and expanding it into more complex systems. But it turns out that in practice, a first order correction is generally sufficient. So unless I'm dealing with really small molar volumes or pressures above, say, 3 to 500 atm, depending on what gas I'm dealing with, I can actually capture most of my non-ideal behavior simply by making use of the first order correction. So this ends up giving me just the B value, or unfortunately what's called the second virial coefficient. First one being 1, second coefficient being B. Now we run into a slight problem, because it turns out that what I have is a Z that will change with the molar volume. And that's actually exactly as we would expect. But we run into a slight problem, because it turns out that our Z should also change with temperature. So we run into a slight problem in that my virial coefficient, so in this case B, should be temperature dependent. So what this means is that in practice, you're going to obtain a set of virial coefficients that will perfectly describe a gas at a fixed temperature. So unfortunately, the Virial equation is mostly going to be best used when describing isothermal behavior. However, if you do know your virial coefficients, we can get a perfect description of our compressibility factor over a wide range of pressures, because we are going to build in that pressure dependence, because remember, molar volume and pressure are indeed related. So, for example, let's go ahead and look at 4 example virial coefficients. Some simple ideal gases like argon and xenon, and some more complex systems like N2 and CO2. So what you're going to notice is that our virial coefficients do indeed show a temperature dependence. So at relatively low temperatures, near room temperature, it turns out that argon, CO2, nitrogen, and xenon all show a negative virial coefficient. Now the question is, what does this end up really meaning? If I've got a negative virial coefficient, this means that my Z value will generally be less than 1. So this means that under low temperatures, all 4 of these gases are going to show a negative deviation from ideal behavior, which is actually fairly useful because it's going to tell me that under these conditions, all 4 of these gases are going to have attractive IMF behavior dominating their interactions. And yes, this does even apply to ideal gases like argon and xenon, though xenon makes a certain amount of sense because it is quite large. But as we increase the temperature to elevated conditions, say 500 Kelvin, what we notice is that argon and nitrogen shifts from a negative to a positive second virial coefficient, which means that their Z values will shift from being positive, from being greater than 1, less than 1, to being greater than 1, meaning that they're going to show positive deviations from ideality. So under these elevated temperature conditions, they're going to become less compressible and exhibit a higher volume than would be expected from the ideal gas equation. Or another way of looking at it, repulsive IMFs or repulsive forces are going to dominate. So their size is more important than their attractive behavior. However, CO2 and xenon are able to form quite stable attractive forces, and so we still see a dominant attractive behavior, even under these high temperature conditions. And I can get all of this simply by looking at the second virial coefficient, which is going to dominate almost all of the non-ideal behavior. And again, we can also reflect back to our more pictorial sense. So what we can do is compare our virial equation to these experimental trends, and we're going to get very kind of similar behavior. So at low temps, we're going to tend to have B values less than 1, or Z's, we're going to have an increased tendency for Z's, for compressibility factors less than 1. At high temps, our second virial coefficient is going to tend to be positive, leading to net repulsive behavior with compressibility factors greater than 0. And then we end up with a very unique position where at our boil temp, so this is going to be the temp at which repulsive and attractive forces essentially cancel out. What we can do is imagining taking the first derivative of our Z with respect to molar volume, which is really going to give us a measure of our B value because our coefficient ends up canceling out, and we're going to see some dependence on our molar volume. And at this point, our B factor should be equal to 0, at least under low pressure conditions. And so this is going to be kind of a very important thing to keep in mind, is that what you're going to be looking for is ideal and near ideal systems are going to have a second virial coefficient as close to 0 as possible. However, you may have noticed that in practice, our virial equation can be a little bit cumbersome, because how often do you go out and measure the molar volume of a gaseous system? So in practice, what we often do is replace a power expansion about the molar volume with a power expansion about the pressure of the system. And so one of the ways you can imagine imagining doing this is switching out our molar volume for a pressure term. So if the system was ideal, these two would have a simple relation uh, of RT. Unfortunately, being a non-ideal system, the conversion in between our two factors won't be quite so simple. But what this does give us is a way to express the compressibility uh, factor sheerly in terms of the much more easily measured pressure. And so you're going to frequently see the virial equation given in terms of pressure instead of molar volume, simply because it's an easier to measure property. And this has a lot of very much practical uses and can be a lot easier to use on an everyday basis. But one of the things I want to make sure that you are very aware of is that both of these equations can often be seen out roaming around the wild. So if you're going to be making use of compressibility factors in, say, your book or online, it turns out that the virial coefficient that you're using may be either B or B prime. And because of poor notation in some resources, a lot of people will report B prime, or my second virial coefficient in terms of pressure, as B. So always be cautious, and when in doubt, check the units to make sure that you have the right conversion, you have the right coefficient, so you're using the right equation. Otherwise, your answers can be quite wrong. So what we saw today was a rather simple tool of how you can take an equation that doesn't work, use a power expansion to go ahead and fix it. And as we go through this semester, you may find that while this might not be the most accurate method, as it does have a temperature dependence that can be difficult to model, it's going to be quite useful and used as a equation of state for correcting some rather complicated system properties as we go into describing energies and other behaviors of gaseous systems. So next time, we're going to be taking a different approach of correcting the ideal gas equation by talking about van der Waals. Till then, take care.